Hello, I'm Ronak Malkan, and this collab is to implement various dimensional reduction techniques. So, first we have to install UMap Learn, which is used for UMap technique, and Plotly will be used to display various metrics as plots. And for this collab, we are using three data sets: digits, iris, and faces. So, digit data set is basically it contains 1700 samples of handwritten digits as images, and it's commonly used for training and testing image recognition models. Then iris is a common data set. It contains samples of flowers which are divided into three categories. And then the faces data set contains 400 images of faces, and like they are divided into different gray scales depending upon the data set. So first we will be exploring the LLE dimensionality reduction technique. So LLE stands for locally linear embeddings, and it is good for uncovering non-linear structures in data. So here you can see that we are trying to fit the data, and we are using the digits data set, and then we are displaying it in form of a scatter plot. You can see the scatter plot here. Then afterwards we are implementing the TSNE technique. So it's particularly suited for dimensional data sets, and therefore we are using iris dataset for this purpose. And afterwards we are doing the same thing. We are plotting the scatter plot for it. The third technique is isomap. Isomap is a manifold learning technique. It's ideal for data sets where data points lie on a curved manifold. So for this we are using the faces dataset. You can see the scatter plot here. The next technique is UMAP technique. It stands for Uniform Manifold Approximation and Projection. It reduces the dimensions while preserving the general structure in the dataset. So we will be applying it on the digits dataset. Then the next technique is MDS. Its full form is multi-dimensional scaling. So it seeks a low-dimensional representation of the data that preserves the distance between every pair of points well. And we'll be using the iris dataset for this technique. Afterwards, there's a technique called PCA, which stands for Principal Component Analysis with a randomized solver. So it is a linear dimensionality reducing technique that uses singular value decomposition of the data, and it only keeps the most significant singular vectors. So randomized solver, because it speeds up the decomposition on the faces dataset which we are using for this purpose. Then there is a kernel PCA technique. So kernel PCA is extension of this technique PCA, and it uses kernel methods to allow for non-linear dimensionality reduction, and we are using the digits dataset here as well. Afterward, there's another thing called incremental PCA. It's also a variant of PCA, so it allows for partial computations which are useful for large data sets like iris. You can see the scatter plot here. And then there is a technique called factor analysis. So it's a method that uh, models the observed variables as a linear combinations of potential factors, and we have used the faces dataset for this. And the last technique is autoencoders. So it's a type of neural network which is used to learn efficient codings of unlabeled data, and that's primarily why we are using the digits dataset for it. So this is the implementation of dimensionality reduction. Thank you.